Okay, now we're rolling. So vector functions. So before we talk about vector functions, what are the kind of functions that we've been dealing with? So here's an example of a function. So really when you talk about functions, it's really about what's the independent variable and what's the dependent variable. Or in other words, what goes in, what set of values do you put in, and what set of values comes out. So what's our independent thing in this? X, right? So x takes on many values. X takes on many values. That's the independent variable. That's what it means, because it varies. X varies. It takes on many values. And then what's the dependent thing? And so that's a real number, right? X is a or scalar. Right? We talked about scalars a lot, right? So scalars versus vectors. A scalar is just a number. It's just a value. Okay, so that's the independent variable. And then what's the dependent variable in this? This is in this here. So what's dependent? What comes out? Or what's the result? For every x that we put in, we get something back. F of x. F of x is the value of the function for the given value of x. And what is that? What kind of thing is that? Is that a scalar or a vector? In your whole, this is your past math career. Scalar, right? You put in lots of values, scalars, and each one of those pops out another scalar, like it maps to or results in another scalar, and that's what we call f of x. So that's in your whole pre-calculus and calculus career. These are the kind of functions you've been dealing with. Real number goes in. For every real number that you put in, a real number comes out. Okay? So what about vector functions? So we want to analyze a vector function the same way. It's got an independent thing and a dependent thing. So here's the form of a vector function. What's the independent thing in a vector function? So r of t equals f of t, g of t, h of t. So what's the independent? But what's the independent thing? What's t, right? T, and that is? T is a scalar, parameter. T varies. It's actually a set of scalars, right? T is a set of scalars. Not scary. So t takes on many values, and as t takes on different values, for each one of those values, what comes out? What's the dependent thing? What do you get according to what you're looking at here? Do you get a scalar or a vector? Vector, right? So so you have a set of scalars, and every scalar is determining a vector. Now, each component is a separate function of t. Each component is one of these old school functions, right? So to get each component, the x component, the y component, the z component, each one separately is one of these old, the ones that you've been doing, right? The put in a scalar, pops out a scalar. Put in a scalar, gives you another scalar. So then when you put those three together, you get a vector, and that's the dependent entity in a vector function. Okay, don't worry about this domain thing. We'll have to cover that. All right, so let me show you an example of a vector function. It's actually Okay, so here's the vector function. They're usually written horizontally, but just for this program that I use, you put them in vertically. So there's all these little conversations going on, like consistently as it's not good. Other people around you could be very distracted by that. So if you want to, every once in a while, you've got something to say, that's okay. You're whispering about the math, that's okay. But just the ongoing comments every 10 seconds isn't going to work, okay? So here's this. I got a cosine for my x component, this polynomial for the y. And then for the z component, 1/2 sine 5t. So that's a vector function. Given every value of t, there's some vector that is produced by that value of t. So when we graph these, what we want to do is put all those, for every value of t, we want to put all those vectors in standard position. So down here at the bottom of the screen, this is how I can control t here. This is a slider down here. So right now t is -1. And so when you plug -1 in, you're going to get some vector, x, y, and z component. And then what we want to do with all those vectors is put them in standard position, put their tail on the origin. So now as you let t increase, every time you change t, you get a new vector. So if you let t increase continuously, you get like a continuous sweep of position vectors. So for every t, there's a vector, let t increase gradually, and you get like a sweep of all these vectors. So then so what we can do then is since the coordinates of the tip are the same as the components of the vector since it's in standard position, right? Remember that? That whatever the components of the vector are, if you put its tail on the origin, then the tip, it's going to have the same coordinates as the components of the vector. So what we're going to do is if we plot all those points at the tip, what kind of thing are we going to get? So, but yes, and what is that? Is that a surface, or what are we going to get when we plot all those points where the tip goes? Is it a surface? Will we get a surface? It's not a surface. Okay, lines are straight, so that line is closer. An arc or a curve. So let's do that. Here we go. Oh, no, didn't do it. So we're gonna track all those vectors in standard position. We're gonna track the tip, and it's gonna generate a curve. So for every t value, you get a point in space. Every t value gives you a point. So let t increase continuously, and you sweep out these points. Yeah. Yes, you could come up with a vector function that would sign your name in cursive. It will. Yes. You could do it. Okay, so this is the way that then this red curve is the way that we represent in R3 this particular vector function that I wrote up there. So another one. Oh, not that one. We'll do that later. I want vector function 2. Okay, here's another one. So here's the x component is this up here. Y, oh jeez, what's going on? Y component is here, z component's here, and so this depends on your view. All right, it's struggling because I got two things running at once here. Okay, so it's cool and you ooh ah, but so just make sure you know what's going on, right? What's going on here? For every value of t, you get an ordered triple, and then let t increase continuously, and it sweeps out all these points, makes a curve. So that's how we represent a vector function. Okay, so let's look at this one that I had built before. So here's one. This is a little more basic vector function. So I've got x equals t, y equals sine 2. So this vector function doesn't have to be called r. Let's call it something else, just so I don't think it. So I can call it c of t. That's perfectly legit. T sine 2t and 1/2 e to the t. Okay, so what do you see that makes this one a whole lot easier, right? What about this vector function simplifies things greatly? X is t, right? And because x is t, and this is y, how could we rewrite y then? What's another way to write the y component? Sine of 2x. So y equals sine of 2x is part of the information of this vector function. It leaves out z, but y equals sine 2x is a relationship that's true about this vector function, right? And how does this graph in space? If you had y equals sine 2x, what would that graph as? Kyle, remember?
I want it to be like a sine wave, but it's like height with double or something.
Okay, it's a sine wave. Okay, yes, right. It's a sine wave with double the. It has half the period, so it's double the frequency, right? So it has half the period. But then how does this graph? If I've got an equation with y and x in it, how will that graph in space? Does anybody remember? If z is missing. What do we call this? This is what kind of thing is this? Cylinder. This is a sinusoidal cylinder. And which way will that extend? So if it's y equals sine 2x, which way will that cylinder extend? Up and down in z, right? It's like if you drew y equals sine 2x and let it go up and down in z, you'd have that cylinder. Okay? So what's true about this curve? This curve is going to completely lie on this cylinder. All the points on this curve will be points on this cylinder. Yeah, question?
So then is this going to be for every cylinder where it's like if the variable that's absent from the equation, then it'll lie on that axis then?
It'll extend infinitely in that direction.
Or in that direction?
Yeah, you could start with it on the, so we can start with this at z equals 0, like in the xy plane. But then z can be anything, so then it extends infinitely up or down in z.
Or if like z was in place instead of x, then it would be.
And then it'd be this, yeah, exactly. Right, so cylinders, the most common types of cylinders, like the ones we've seen, are equations of 2 of the 3 variables, and then it runs infinitely in the direction of the third variable. Yep. Okay, so now look what happens then. If I take, don't miss this. So I'm going to grab this, and I'm going to look. How can I see this then? What view should I take so that z is gone? What view should I take so that z is missing? From above, right? If I look straight down, then z is not part of my view. So here we go, ready? So I'm going to take this and look straight down the z-axis. But it shouldn't be surprising because that's what the math said, right? If I just combine x and y and ignore z, I get this equation. So there it is. So mathematically, it makes sense. If I ignore z, that's what I'm doing by looking down the z-axis. I'm ignoring z, so I'm going to get this relationship y equals sine 2x. Okay? What other relationship then is part of this vector function? What's another one? Tell me. What about e?
1/2 e to the x.
What is 1/2 e to the x? Z equals?
1/2 e to the x.
What kind of surface is that?
Spiral.
Z equals 1/2 e to the x. Tyler, what kind of surface is that? Okay, so this is exponential, and then what happens when you have just two variables? It's a cylinder, right? This is an exponential cylinder that runs. It's going to run parallel to the y-axis, right? How can I see that? So, yep, so I'm going to lift this. This is my y-axis. This is my y-axis going up here. So I'm going to lift it up, so I'm looking straight down it. And I got to do it here. And so I'm looking in the what plane am I looking at then? The xz plane. So now I'm looking straight down the y-axis. X is to the right, z is up. And so then I see this. Okay, what other surface? So there's another surface that I have. What's the last surface that I have? So how can we combine y and z? What would we need to do to combine y and z? Z equals 1/2 e to the t. What do we need to do then to get this to work? Solve for t, right? So 2z equals e to the t. What does t equal? It's the inverse of e. Does anyone know the inverse of e? Natural log of 2z. And therefore, what can I write? Not x. Y is equal to sine of 2 times ln of 2z. Whatever that is, right? It's something very unfamiliar. Who knows what that is? But how can we find out? We know exactly now how to find out what that curve looks like. Can look straight down the x-axis, right? Get x out of the picture. Just look at y and z. It's going to take me a second. There we go. Get in there. Sorry. I had it. I was so close. Okay, almost there. There we go. So what happens here is, for low values of z, lost here. Something like that. This is hard to control. Oh man. Stop now. Let's just stop. Okay. Close enough. Okay, so what happens is for low values of z, you get lots of cycles of sine. But then as z increases, this exponential takes over. And so you're going to get, z is going to increase rapidly as t increases. And so then you don't see as much variation in the y coordinate sign. So that's just going to get like infinitely squiggly as you get close to the xy plane there. Okay, so one way to help you sketch these curves is to isolate two of the variables and come up with the equation of those two variables, and you know that will be like the projection into that plane. So the projection into the xy plane, or the cylinder that it lies on, is that y equals sine 2x. So that can help you trying to make sense of what the curve's going to be like. So that's looking down on the xy plane. It's be y equals sine 2x. And then looking down at at the xz plane, you get the exponential curve, y equals 1/2 e to the x. So that's one technique that can help you make heads or tails of these. All right, so let's do a couple of easier examples here. Let's see what else we got. So how about the vector function t squared -3 and t. Or let's do, well, let's change that. Let's make that t and this t squared. Okay, let's see if we can sketch this without any technology. Let's see if we can figure out what this looks like. Technology is not a replacement for your brain, though. So we want to exercise our brain. On easy ones like this, we should be able to figure it out, put it together. So right away, we got a big clue about what's going on with this one. What can we say right away? And what will that mean? Good, Colin. What will that mean if y is equal to -3? Okay, if y is -3, what is y equals -3? So what? How would that graph in space? Y equals -3.
All those points are going to be parallel with the x-axis at y equals -3.
Okay, right. So at y equals -3, a plane, exactly. So y equals -3 is here. So this curve is going to lie entirely on that plane, which is parallel to x. You can do better than the x-axis. Parallel to xz plane. So that's the plane y equals -3. Going through this point. So the curve will lie entirely on that. Okay, what else can we do now? So
z equals x squared.
he wants z equals x squared. If x equals t, then does z equal x squared? Lucas says yes. David, what do you think? They're saying z equals x squared. Is that what this tells us? Yeah. So if x equals t, then we can, then this is z, and it equals x squared. Okay, what does that look like? So now that's going to help us, right? We know we're lying totally in y equals -3. What will z equals x squared look like? Parabola. Vertex at?
At -3, at y equals -3.
Right, when x is 0, z is 0, and we know we're in y equals like -3, so the vertex is there. Which way does it open?
Both ways. Upward.
Okay, so let's put it in. Now let's use technology to, a good use of technology here would be to check it. So we got t, -3, and t squared. So it won't be in the same place. I don't know exactly where -3 was here on my scale, but it should be the same. So you're using previous knowledge, and so a big thing is, looking for these obvious clues like the y equals -3. Well, that just isolates the curve right on the plane y equals -3. And then the rest of it will be whatever curve you get with z and x. So z equals x squared. It's just our basic parabola, and it will be in the plane of y equals negative 3. Okay, another example. How about cosine t, 2 sine t, negative 2. All right, so Elena, any ideas about this one? Just anything you can say about this. Okay, so what will that mean for our curve if z is negative 2? And use your hand to show me what that plane is like. Yeah, right. So 2, it's going to be in the plane, what, 2 units below the xy plane. Down here somewhere. Does that look like 2 units below? If you drew it like that, I'd be thrilled. That's looking pretty good. Okay, now we got to figure out what's going on here. Do we want to solve for t and plug it into the other one? Nah, because then we'd have like inverse cosine or inverse sine. We want to avoid that. So we want to think about something else here. If you have 2 variables and one is cosine and the other is sine, what is that? So I got x equals cosine t, y equals 2 sine t. Chandler, you know what that is? If you got 2 variables and one is assigned cosine, the other is assigned sine.
So they're like derivatives and antiderivatives.
Okay, true. Giorgio, what do you think? If one variable is assigned cosine, another variable is sine, and you graph that in that plane, what do you get? We're just in a plane though, right? So don't jump ahead. So we're just in the xy plane. So you can't get a corkscrew in the xy plane, right? What's that? So each one of those separately would be one of those, right? Assigned. But when you parametrically you put x as cosine and y as sine. Anybody remember what you got? Yeah.
I know on the unit circle, x is cosine, y is sine. So you
Right.
just get like a unit. What do you just get a circle?
Right, you get a circle, right? Because the definition of cosine is what? The x coordinate on the unit circle.
So
And the definition of sine is the y coordinate on the unit circle. So if you pick any, if you pair up, are you saying you should have known that? Is that where you're?
Yeah.
Okay. Right.
Oh, unit circle.
Right.
Unit circle.
So, but this is a little bit different.
Because it's got the two.
So what will the 2 do?
You're just gonna stretch out the radius of the circle.
Stretch it out so that you get an? Okay, what's a mathematical oval? Ellipse, right? So this is an ellipse. We're going to get an ellipse. And is it going to be wider left and right or wider back and front?
Wider left and right.
Wider left and right. So the radius in the x direction is? 1. Radius in the y direction is? 2. There's your ellipse. And where does it live? Z equals negative 2. All right, let's do it. Let's see. So there's my ellipse, 2 in the y, 1 in the x. It lives in z equals -2. Doesn't make sense. Okay, your turn to practice. Now I got some practice problems.
Did say over.
Okay, so here's 4 to start with. Let's do these. So when you write these, you write them horizontally. Don't copy the way they look. So when you write out vector functions, you write in a vector, chevrons, and then write x, comma, y, comma, z. Okay? So you write those out. So we're like kind of gathering a toolbox for these, right? So we know if we could isolate a t and pair up the variables to make equations of pairs of variables. We're looking for sine and cosine. We're looking for, what else are we looking for? Yeah, combining variables and thinking about them being projected into their respective plane. So there's kind of like, there's no one way to do these. You have to kind of use a bunch of different tools, whatever applies at the time. Yeah. What do you think? So when I wrote this, do you recognize that as something we've done before?
Yeah.
What is? Parametric equations of a line. And that tells you 2 things right away about the line. Caden, what does it tell you about the line? Yeah, right. So what's the point? 1, 0, -2 is on the line, and then 3, -1, 1 is parallel to the line. So we already did one type of vector function in this class. When we were doing lines, we were doing a specific type of vector function, a linear vector function. Okay, so we'd already done this kind of before today. All right, so let me give you a little tip on drawing the direction vector. So let's start over here. So from that point, first of all, don't make it so steep. So from that point, so kind of like march. So from there, you're going to march forward. Yeah. How far are you going to march forward in the x direction? 3. So just do like dot, dot, dot. From there, parallel to your x-axis. Bigger. No, bigger. This is 2, right? So
yeah.
Your 1 is like that. So
1, and then 2.
And make dots. Just go 1 along there. Yeah, there you go. 1,
2, and 3.
Good. Okay, and then from there, you're gonna go
And -1
to the left. 1. No, from there, from where you were.
Okay.
But okay.
And then +1
There.
right there.
Now draw the line. There you go.
Okay.
It's both ways. All right, let's put it up. See how we did. Is that about what we were thinking about? Okay, so that's that line through 1, 0, -2 with direction vector 3, -1, 1. Good. Next, Giorgio.
So the function was sine t 0 cosine t. So since y is 0, that means it's going to be on the plane that is y equals 0. So it's going to be parallel to the xz plane. And since it's a sine and cosine function, so it's going to be a circle and of the radius 1. So it's a circle on y equals 0 and the xz parallel to xz plane. I don't know if you can see those. This plane right here.
So he's saying it's a circle in the x or circle in x and z. Agree with that? Yep. Sine, cosine, and two variables makes a circle. Okay. And then he said it's. What are you saying? Is it parallel to the yz plane, or parallel to the xz plane?
Well, it's on the axis because y equals 0.
Right. Y equals 0 means it's on the xz plane. So let's draw that one. Here we go. Ready? Boom. Is that what you imagined or drew? That's what you should have imagined and tried to draw. That right there. Next, Colin, number 4.
Okay, so this we have x coordinate of 2, which means that it's going to be a plane at 2 on the x-axis, and then because y equals t, and z is equal to b of t, then that means it's an exponential function. Then if we twisted it so that we saw the z-axis and the y-axis, it would be an exponential function on that plane.
What do you guys think?
Because it's sorry, I'm terrible at this.
That's okay. So in terms of where the plane is, can you talk about where the plane is, like relative to the board? So where's the plane relative to the board that you drew on?
I know it's a bit hard to tell.
No, it's okay. Just verbally.
Well, it would be like relative to the board. It would just be 2 away from the origin, right here, towards. It would be coming towards the board. So if that makes sense.
That's okay.
Dang.
So where is x equals 2 relative to the board? David. David. Parallel to. Yeah. Yeah, the board is the YZ plane. So it's a plane that's 2 units in front of the board.
Yeah.
And then your exponential function will lie on that. So let's draw that one. Is that what he drew? Perfect. So it's the exponential z equals e to the x in the plane, sorry, z equals e to the y in the plane x equals 2. Last but not least, Ryan.
First thing I noticed was that z is constant, so it's going to lie in the xy plane only. But at z equals 3, the y function is squared, so it's an absolute value. So it's always going to be positive, negative. And then x is just straight up t, so it can be plus or minus x. So you're going to have a parabola that goes, I think, from like me towards the board and then back out and away. Like if somebody like down here threw a boomerang, it would.
What do you think?
Exactly.
So the picture's beautiful. Is it right?
Yeah.
Okay. What about the equations? Could we do that? Could we have done that a little more like efficiently, or instead of the absolute value and the plus or minus x? Is there a more efficient way to do that?
So my thought was that. It's always already x my school of thought here was plus t.
That's the line.
I thought maybe I could model it.
If x is t and y is t squared, how can we simply express that together? If x is t and y is t squared, then y is
Y equals x squared.
y equals x squared, right? That's probably going to be your most efficient way of expressing the x and y together.
That makes sense.
So does that agree with your graph?
Yep.
Ryan? Y equals x squared? Does it? Does y equals x squared agree with what you drew?
I hope so.
Your hopes were not misplaced.
Okay, let's do, so these are good starting point, but let's do something more interesting.
Yeah, I'm good. We've accomplished one.
These two. Go.
One set value.
Yeah, or the y-axis is then it's gonna be going up and down. The z-axis. Yeah, it's gonna be moving up. Take a look at it's gonna be a circle that just goes up and down.
I think because
Like that?
it's not going to be it's just like because you can write the
It'd just be a circle that just goes on the.
I believe.
Remember, like whatever variable.
So the goal
It only works when we have the circle. Cosine t but I don't like it'd be like 2 sines of it.
Okay, anyone have an epiphany about this? Brandon over here. Do you guys? What do you think? What'd you guys talk about?
Well, we were saying that like y is equal to like 2 sine of z, and then x is also the cosine of z.
Okay.
That's about as far as we got.
David.
I have a question about like drawing these graphs. So maybe you just draw a sketch, say parallel to the xy plane, and then the xz plane, yz plane. Just combine.
Yeah, so we kind of talked about that, combining two variables at a time, and then each one of those will be the projection of the curve into its respective plane. So that's one that's part of the technique to do this. But there's kind of several little things that we're using that we're pulling from to sketch these. So rather than, x equals cosine of z, I think there's a Sebastian.
Can't you just, since z equals t, it'll be on the either the x or the y-axis, because it's essentially saying the z-axis isn't going to be a factor on it, so you can just write it as an xy plane, and the circle exists on that origin.
I'm not sure I understand that. Max, you got an idea?
I just see that there's a circle that's going to be forming.
So when you say you see a circle, what do you mean?
X is going to be cosine of t.
Okay.
2 sine of t. It's going to be like the circle we drew earlier.
Okay.
It's going to be like a regular circle, but the line just stretching out like this.
And so what's that called? That's an ellipse. So I think this is a good way to start. In the XY view, of this, you have the ellipse, right?
So it's an oval, and then for every t.
And how does the ellipse get generated? As t changes, we get points around the ellipse, right? As t increases, it like draws out the ellipse. But now what else is happening? Right, as t increases, then what's happening to z? So if I do this, this is t increasing around the ellipse, and now I also make z increase. What will I get?
That's the corkscrew.
That's the corkscrew, right? So as t increases, I get the points on an ellipse, but then z is also increasing as you're doing that.
Yeah.
Spirals up and the axis.
So how do I see the ellipse? What do I do to see the ellipse?
Go in the xy.
Cancel out z, just look down the xy plane. There's the ellipse. Okay, what about x equals cosine t? Can I see that? X equals and that was just cosine z, right? So if t is z, x equals cosine z. will be, look down the y-axis. Here's x equals cosine z. And then what about, do we have y equals sine 2z? Don't we have y equals sine 2z? Ah. So there's y equals sine 2z. But each of those, what are those really graphs of in space? What are each of those? So say, oh, and if this is an ellipse, what's the x radius?
0.1.
And what's the y radius? So I just should divide by 4 equals, or 2 squared equals ellipse 1, right? Remember? So this is just like a two-dimensional ellipsoid is an ellipse. So x radius, y radius. What about, and we said what? That x equals what in this? What relationship do we have x equal to? Cosine of z. I don't know how that happened. It's cosine z, and then, gee whiz. What is going on? I keep hitting 0, I guess. All right, and then y equals?
Y equals 2 sine z.
So each of these individually, what are these things? What is that in R3? I've got an equation of 2 variables. What is that? Cylinder, elliptical cylinder. What's that? Another cylinder, that's a sinusoidal cylinder. So those projections that I showed you by turning the axes, if you extend them in the other variable, you get a cylinder, right? You get a cylinder. So what is the relationship of the curve to those 3 cylinders? If I graphed all 3 of those cylinders, then what would the curve be? Points on all 3 cylinders, right? So it's what related to the surfaces? The curve is, what's that? It's the intersection of these 3 surfaces. You ready? Should we graph them all at once? So the green one, the green one is my y equals sine 2z. The gray one is my x equals cosine z. And then I've got the gold one is the elliptical cylinder. So then the intersection of all 3, I'll have to make it a little bigger here. Does it show up? The blue show up? Yeah. The intersection of all 3 surfaces is that curve. So that curve, it lies on both sinusoidal cylinders, and it lies on the elliptical cylinder. So it's the intersection of all 3 of those surfaces. Okay, what about this one? So t cosine t and t sine t, is that a circle and an ellipse? No, go ahead.
That would be open and wide.
It's a circle that slowly expands the farther away it gets
Good.
from the y-axis.
Nice.
So
I kind of draw
Ah.
like this. Like this. And so like it will slowly loop around and then slowly go out.
Okay, and then you got around a parabola in the y. Not bad idea. So let's, that's good. So in x and z, it's going to go around in a circle, but as t increases, that circle's going to get bigger, right? Right? So it's gonna like spiral out like this. But then y equals t squared. So as t increases, so it's going to be like not in a parabola, but so this next thing I'm going to show you is a really important technique. When you have cosine and sine, how can we combine those to make them go away? How can we combine cosine and sine to make them go away? Anyone remember from the trig? Well, then you got tangent. So I want it to go away. So cosine squared, sine squared equals 1. That's the Pythagorean identity. We're going to use that here. We're going to use that here. I'm going to take x squared plus z squared. And that's going to get me cosine squared and sine squared. Do you see it? So x squared plus z squared equals t squared cosine squared plus t squared sine squared. And what does that equal? Take out a t squared. What am I left with? 1. But what is t squared equal to? Y equals? What's that? Nope, it's not cylinder. Paraboloid. So if the x, y, and z are related in this way, then that curve lies on this paraboloid. That curve lies in this paraboloid. And it does, so that's what we said. We said that as t increases, it'll make bigger and bigger circles, but then as t increases, you'll get bigger y. So it'll be like this. And that'll be the paraboloid. Let's see it. And we'll be done. Turn these off. So in doing these problems, going back and forth between surface and curve, this is an important technique. Using the Pythagorean identity to get rid of your t. So cosine squared plus sine squared goes away. Here we go. Let's see it. So that's like it's like a corkscrew, but now this corkscrew it lies on the paraboloid y equals x squared plus z squared. So it's bigger parabolically as you go out the y-axis. Okay,